why solid objects are not solid. Pick up anything near you right now. A pen, a cup, your phone. Feel it, it's solid, right? Hard, dense, real. You can knock on it, you can feel its weight. You can trust it to hold its shape. That object, whatever it is lying to you. It is not solid, not even close. And I don't mean this in some poetic hand-wavy sense. I mean it in the most literal, physical, experimentally verified sense possible. The thing you're holding is almost entirely empty space. And the tiny fraction that isn't empty space isn't really solid either. It's something far stranger than anything you've been taught. I'm Leonard Susskind, and I've spent over 50 years studying the fundamental nature of matter. And I can tell you with absolute certainty that solidity, the feeling of hardness, the sensation of touching something real, is one of the greatest illusions in all of physics. An illusion so complete, so convincing, that even most scientists walk around their daily lives forgetting it. Let me show you what your coffee mug is actually made of. And I warn you, by the time I'm done, you'll never look at the physical world the same way again. Let's start with the atom. You probably learned in school that everything is made of atoms. That's true. Your coffee mug, the table it sits on, the air around it, your hand that grabs it, all atoms. And you probably learned that atoms are small, very small. But here's what they almost certainly didn't tell you. Atoms are mostly nothing. If you took a single atom of carbon, one of the most common atoms in your body, and blew it up to the size of a football stadium, the nucleus, the dense core, where almost all the mass lives, would be some marble sitting at the center of the 50-yard line. The electrons would be somewhere in the upper decks, tiny specks, each one far smaller than a grain of sand, orbiting that marble at the center. And everything else, the seats, the field, the corridors, the parking lot, all of that would be empty, completely empty. There's nothing there, no substance, no material, no stuff, just vacuum. This isn't an approximation, this is the actual ratio. The nucleus of an atom has a diameter of about 10 to the minus 15 meters. The atom itself, defined by its electron cloud, has a diameter of about 10 to the minus 10 meters. That means the atom is about 100,000 times wider than its nucleus. In terms of volume, the nucleus occupies about 1/trillionth of the atom's total volume, 1 part in a trillion. Everything else is empty space. So when you're holding your coffee mug, what you're actually holding is a collection of trillions upon trillions of atoms that are themselves trillions of times more empty than full. If you could somehow squeeze out all the empty space in your body, collapse every atom down to just its nuclear material, you would be smaller than a grain of sand. The entire human race, all 8 billion of us, compressed to nuclear density, would fit inside a sugar cube. That's how empty matter is. That's how empty you are. Now, you might be thinking, okay, Lenny, atoms are mostly empty. I've heard this before, but the mug still feels solid. I can't put my hand through it. So something must be filling that space, and something must be making it hard. And you'd be right to think that. But the answer to what makes things feel solid is far stranger than empty space being secretly full of something. The answer is forces, specifically electromagnetic forces. And this is where physics gets truly beautiful and truly weird at the same time. When you press your hand against the table, your hand never actually touches the table. Never, not even a little bit. What happens is this. The electrons on the outermost shells of the atoms in your hand get close to the electrons on the outermost shells of the atoms in the table, and those electrons repel each other violently. Electrons carry negative charge, and like charges, repel. This electromagnetic repulsion is incredibly strong at short distances. It pushes back against your hand with enormous force. That force is what you interpret as hardness. That force is what you call solid, but there's no contact, there's no touching. There's just two clouds of electrons screaming at each other across a tiny gap of empty space, refusing to get any closer. This means you have never touched anything in your entire life. Not your mother when you were born, not the food you eat, not the ground you walk on. Everything you've ever experienced as touch is electromagnetic repulsion between electron clouds that never actually make contact. The sensation of solidity is a lie told to you by your nervous system, a useful lie, an essential lie for survival, but a lie nonetheless. And here's what makes this even more disturbing. There's something called the Pauli exclusion principle. This is one of the most important principles in all of quantum mechanics, and it's absolutely essential for understanding why matter appears solid. The Pauli exclusion principle, named after the physicist Wolfgang Pauli, states that no two fermions can occupy the same quantum state simultaneously. Electrons are fermions. So when two atoms get close together, their electrons cannot simply overlap and merge. They're forbidden from doing so by the deepest laws of quantum mechanics. Each electron must maintain its own distinct quantum state. This creates what physicists call degeneracy pressure, a quantum mechanical force that resists compression and gives matter its apparent rigidity. Without the Pauli exclusion principle, there would be no chemistry, no solid objects, no you. Every atom would simply collapse into its nucleus, and matter, as we know it, would not exist. Think about that for a moment. The solidity of your desk, the hardness of diamond, the rigidity of steel, none of it comes from atoms being packed tightly together. It all comes from a quantum mechanical rule about electron identity. The universe doesn't care about providing you with a comfortable surface to set your coffee on. The universe has rules about how identical particles behave, and as a side effect, an accidental consequence of those rules, you get to sit in a chair without falling through the floor. But here's where things get really interesting. Let's go deeper, much deeper, down past the atom, past the electrons, into the nucleus itself. Because if you thought atoms were strange, you haven't seen anything yet. The nucleus is made of protons and neutrons. You learned that in school. Protons carry positive charge, neutrons are neutral. They're packed together in the center of the atom, and they account for more than 99% of the atom's mass. But what are protons and neutrons made of? They're made of quarks. Each proton contains 3 quarks, 2 up quarks and 1 down quark, bound together by the strong nuclear force mediated by particles called gluons. And here's the astonishing thing. The quarks inside a proton account for only about 1% of the proton's mass. Let me say that again. The quarks, the fundamental particles that supposedly make up the proton, contribute only about 1% of the proton's mass. Where does the other 99% come from? It comes from energy. And specifically, it comes from the energy of the gluon field, the strong force interactions binding the quarks together. Einstein's famous equation, E equals mc squared, tells us that mass and energy are equivalent. The energy of the strong force field inside the proton manifests as mass. Your coffee mug's mass, your body's mass, the mass of every object you've ever lifted or weighed, 99% of it is not stuff in the traditional sense, it's pure energy. It's trapped, confined, seething energy of the quantum chromodynamic field. So here's the picture. Your coffee mug is made of atoms. Those atoms are 99.9999999% empty space. The tiny nuclei at their centers are made of protons and neutrons, whose mass is 99% energy rather than matter. The quarks that make up those protons and neutrons are point particles with no spatial extent whatsoever as far as we can measure. And the reason the mug feels solid has nothing to do with physical substance and everything to do with electromagnetic forces between electron clouds that never make contact. The solid world is an illusion built on emptiness, maintained by forces, and given mass by energy. You're drinking coffee from organized nothing. Now, let me take this even further. Because we haven't hit the bottom yet. What are quarks and electrons actually made of? This is where modern physics reaches the edge of what we understand. And what we find there is perhaps the strangest idea in all of science. Quantum field theory, our best description of fundamental reality, says that particles are not tiny balls of stuff. They're not little marbles. They're not even really things in any meaningful sense. Particles are excitations of underlying quantum fields. Think of the ocean. The ocean is a vast body of water stretching in all directions. Waves form on its surface. Those waves have energy, they have momentum, they have definite shapes and sizes. But the waves are not separate from the ocean. They are the ocean temporarily organized into a particular pattern. Hence, in quantum field theory, the entire universe is permeated by fields: the electron field, the quark field, the electromagnetic field, the gluon field, the Higgs field, and several others. Hence, these fields exist everywhere, at every point in space, at every moment in time. And what we call particles, electrons, quarks, photons are just ripples in these fields, temporary disturbances, hence localized vibrations. An electron is not a thing sitting somewhere in space. An electron is a particular vibration pattern in the electron field. A photon is a vibration in the electromagnetic field. Hence, a quark is a vibration in the quark field. And these fields are not made of anything more fundamental, as far as we know. They're the ground floor of reality. The fields are reality. Hence, everything you see, everything you touch, everything you are is a pattern of vibrations in quantum fields. There is no substance underneath. There is no solid ground at the bottom of reality. Hence, just fields vibrating in the void. This is not speculation. Hence, this is the standard model of particle physics, confirmed by thousands of experiments, tested to extraordinary precision, responsible for every prediction we've ever made about subatomic phenomena. Hence, the solidity of matter is not just an illusion in the sense of atoms being mostly empty. It's an illusion in the sense that matter itself is not where you think it is. There are no little balls. Hence, there are no tiny building blocks. There are only fields and their excitations, vibrations in mathematical structures that permeate all of space and time. Let me give you an analogy that might help. Hence, imagine a perfectly still pond. The surface is flat, featureless, calm. Now imagine you disturb the surface. Ripples form. Those ripples interact with each other. Hence, they can combine, interfere, bounce off obstacles. Hence, if you looked only at the ripples and knew nothing about the pond underneath, you might conclude that the ripples are things, objects with definite properties. Hence, you might give them names, measure their heights, track their speeds. You might even build a theory of ripple mechanics, but you'd be missing the deeper truth. The ripples are not things. Hence, they're patterns in the pond, and the pond itself is the real story. That's what quantum field theory tells us about matter. The particles are not the story. The fields are the story. Hence, and the fields are not made of anything solid. They're mathematical structures described by equations existing in a framework we call space-time. Hence, what you call a solid object is a particular stable configuration of field excitations bound together by force-carrying field excitations, giving rise to electromagnetic interactions that your nervous system interprets as hardness and texture and weight. Now here's something that should really disturb you. The vacuum, empty space is not empty. This follows directly from quantum field theory. Hence, the fields are always there. Even in supposedly empty space, the fields are fluctuating, they're jittering with quantum uncertainty. Virtual particles are constantly popping into and out of existence. Hence, pairs of particles and antiparticles appearing from nothing, existing for an impossibly brief moment, and then annihilating each other. Hence, this is called the quantum vacuum, and it's one of the most energy-dense environments in the universe. Hence, the energy of vacuum fluctuations is theoretically enormous, though its gravitational effects are puzzlingly small, a discrepancy known as the cosmological constant problem, one of the biggest unsolved problems in all of physics. But the point for our discussion is this: the distinction between something and nothing, between matter and empty space, is far blurrier than you think. Hence, matter is organized vibrations and fields. Empty space is the same fields in their ground state, still fluctuating, still dynamic, still fizzing with quantum activity. Hence, the difference between your coffee mug and the space next to it is not the difference between something and nothing. Hence, it's the difference between two different states of the same underlying quantum fields. One state is organized into atoms and molecules and ceramic. The other state is what we call vacuum. Hence, but both are states of the same fields. Both are something. This raises a philosophical question that I think is profoundly important. Hence, if solid objects aren't solid, if matter isn't really material, if particles are just vibrations, and if even empty space is full of quantum activity, then what is real? Hence, what does it mean for something to exist? Physicists have been wrestling with this question for 100 years, ever since quantum mechanics first revealed the weirdness of the subatomic world. Hence, And honestly, we still don't have a complete answer. Some physicists, like myself at various points, have argued that the mathematics itself is the fundamental reality. Hence, the fields described by our equations are not analogies for something deeper. They are the deepest thing there is. The universe is mathematical structure. And others argue that there must be something more, some ontological substance underlying the mathematics, some real stuff that the math describes but doesn't constitute. Hence, I don't think this question is settled. Hence, but what I do think is settled, what the physics makes absolutely clear, is that the everyday intuition of solidity, the common sense notion that objects are made of hard, impenetrable stuff, is hence wrong, completely, thoroughly, irrevocably wrong. The desk you're sitting at is a force field masquerading as furniture. Hence, your body is a self-organizing pattern of quantum vibrations pretending to be a person. Hence, and the ground beneath your feet is a thin crust of field excitations hovering over a molten core, spinning through space around a nuclear furnace, hurtling through a galaxy that is itself mostly empty space. Let me talk about something specific that illustrates just how strange solidity really is at the quantum level, quantum tunneling. This is a phenomenon where particles pass through barriers that they should not be able to pass through according to classical physics. If you throw a ball at a wall, the ball bounces back. Every time, without exception. But if you fire an electron at a thin barrier, there's a probability, a non-zero calculable probability, that the electron will simply appear on the other side. Not by going over the barrier, not by going around it, not by breaking through it. It just appears on the other side as if the barrier wasn't there. This is quantum tunneling, and it happens because particles are not little balls. They're wave functions, probability distribution spread out in space. And when a wave encounters a barrier, part of the wave can leak through to the other side. If the barrier is thin enough, enough of the wave gets through that there's a measurable probability of finding the particle beyond the barrier. Quantum tunneling is not theoretical speculation. It's the basis of real technology. The tunnel diode, invented in the 1950s, works entirely on tunneling. Flash memory in your computer relies on quantum tunneling to store and erase data. The scanning tunneling microscope, which can image individual atoms, works by measuring the tunneling current between a sharp tip and a surface. Nuclear fusion in the sun depends on quantum tunneling. Protons in the sun's core don't have enough energy to overcome the electromagnetic repulsion between them. They shouldn't be able to fuse, but they do because they tunnel through the Coulomb barrier. Without quantum tunneling, the sun wouldn't shine, you wouldn't exist. And here's the thing about tunneling that relates to our discussion of solidity. Tunneling means that on a quantum level, barriers are not absolute, walls are not impenetrable. The solidity you feel when you push against a table is a statistical effect. The overwhelming probability that the enormous number of particles in your hand will not tunnel through the enormous number of particles in the table. But the probability is not exactly zero. It's fantastically, absurdly, laughably small. And so small that if you pushed against a wall continuously for the entire age of the universe, the probability of your hand tunneling through would still be effectively zero. Trillions of times less likely than winning every lottery on Earth simultaneously, but it's not zero. In principle, quantum mechanics allows your hand to pass through a solid wall. In practice, the statistics of large numbers make it impossible. But the fact that it's even theoretically possible tells you something deep about the nature of solidity. It's not fundamental. It's statistical, it's emergent. And this is really the key insight. Solidity is an emergent property. It emerges from the behavior of enormous numbers of quantum particles interacting through electromagnetic forces and obeying the Pauli exclusion principle. No individual particle is solid. No individual atom is solid. No individual molecule is solid. Solidity only appears when you have unimaginably large numbers of these entities acting together. It's like a crowd at a concert. No individual person is a crowd. But get enough of them together and you get something with its own properties, its own behavior, its own dynamics, properties that don't exist at the level of any individual person. Solidity is the same. It's a crowd effect, a statistical phenomenon. An emergent illusion created by the collective behavior of particles that are themselves nothing more than vibrations in quantum fields. There's one more thing I want to talk about, and it's something that connects the illusory nature of solidity to the largest structures in the universe: neutron stars. When a massive star runs out of fuel and its core collapses, protons and electrons are crushed together by gravity to form neutrons. The result is a neutron star, an object about 20 kilometers across containing more mass than our sun. On a neutron star, normal matter has been crushed to nuclear density. All the empty space inside atoms has been squeezed out, the electron clouds have been forced into the nuclei. What remains is essentially a giant atomic nucleus, 20 kilometers wide. A teaspoon of neutron star material would weigh about 1 billion tons. This is what matter looks like without its illusion of solidity. When you remove the empty space, when you collapse the electromagnetic barriers, what's left is incomprehensibly dense, incomprehensibly extreme, and nothing like the comfortable solid world we inhabit. And even neutron stars aren't the end of the story. If you compress matter further, beyond even nuclear density, you get a black hole. A singularity where the known laws of physics break down entirely, where matter ceases to be matter, where space and time twist into something we don't fully understand. The progression is telling everyday matter, mostly empty space held together by forces, compress it and you get nuclear matter, extremely dense but still recognizable as stuff. And compress further and you get a singularity which isn't stuff at all, just a mathematical point where our equations give infinities. And what this progression tells me after 50 years of thinking about it is that solidity is not a fundamental feature of the universe. It's a phase like ice is a phase of water. And at low energies, at the temperatures and pressures where we live, quantum fields organize themselves into atoms and molecules that interact electromagnetically to create the illusion of solid surfaces. But change the conditions, heat things up to millions of degrees, compress them under the weight of a collapsing star, accelerate them to nearly the speed of light in a particle collider, and the illusion dissolves. The fundamental reality is fields, forces, and energy, not solid stuff. I know this is uncomfortable. We are creatures of the solid world. Our entire existence depends on the reliability of solid ground, solid walls, solid food. Our brains evolved to navigate a world of objects, to distinguish hard from soft, rough from smooth, heavy from light. These categories are useful, they're essential for survival. But they're not fundamental. They're not what the universe is really like at its deepest level. At its deepest level, the universe is not solid. It's not made of stuff. It's made of mathematics and fields and symmetries and conservation laws and the strange, beautiful, terrifying logic of quantum mechanics. And the fact that this seething quantum chaos somehow organizes itself into a cup of coffee sitting on a table in front of you is, to me, far more amazing than if the cup were simply made of little hard balls stuck together. Could I be wrong? Could there be some deeper level of reality where solidity is fundamental? Where particles really are tiny, hard objects? I suppose it's possible. The history of physics is a history of surprises, but everything we know, every experiment we've done, every theory we've confirmed, points in the same direction down, deeper into more abstraction. More mathematics, more emptiness, more fields. The solid world is the surface. Underneath it, there's an ocean of quantum strangeness that doesn't look anything like a desk or a coffee mug or a human hand. So the next time you pick up something solid, something heavy and hard and undeniably real, remember what you're actually holding. A cloud of quantum fields vibrating in patterns held together by electromagnetic forces across vast stretches of empty space, given mass by the energy of the strong force, obeying rules written in the language of mathematics, creating the sensation of solidity through nothing more than the statistics of incomprehensibly large numbers. You're holding organized nothing. And that organized nothing is the most extraordinary thing in the universe. Not because it's solid, but because it isn't. And it convinced you otherwise for your entire life. That's what physics teaches you. Reality is not what it appears to be. And after 50 years of looking beneath the surface, I can tell you what's actually down there is far more beautiful, far more strange, and far more magnificent than the solid world we think we live. And thank you for listening. Now go pick up your coffee mug and think about what you're really holding. Think about the emptiness, the forces, the fields. Think about the fact that nothing in that mug is touching anything else, and welcome to the real universe.